So, okay, so, hmm, okay, good day, guys. So, good day. So, yes, we're going to start our lesson now. So, last time we finished in our lesson, which is errors, right? Thumbs up if we finished errors. So, among of you uh, have read recap of errors. Is it errors, right? Right? Thumbs up tayo. Thumbs up, thumbs up. Errors. Okay, okay. So thank you to all those students who uh, raised their thumbs. Okay, so if after we finished errors, so before we proceed to another lesson, let's have a short recap. Okay, short recap of what we just discussed last time. Errors. We have two types of errors. Two types: the systematic and the random error. So when we talk about the systematic errors, we have the instrumental errors, the personal errors, and lastly the external errors. So when we talk about instrumental errors, it is the fault of our apparatus. Okay, so the apparatus is faulty. That's why we don't get a good reading of measurements and results. Okay. So when we talk about now the personal errors, it is the errors of a person. So this is a human fault. Nothing to blame, not the machine, not the weather, but just the plain human fault. Okay? Next thing is we have the external error. So this is not the errors committed by our instruments nor the people nor the person, but this is an uncontrollable environment. So when you talk about external errors, it is caused by nature, normally by nature. So next is we have the random errors. So when we talk about random errors, it is or it can be positive or it can be negative in result. Okay, so we don't know if it will happen positively or negatively. It relies on observation, research, and statistics. Okay, so that is the random errors and systematic errors. Now we proceed to precision and accuracy. When we talk about accuracy, it is a state, the state of being correct. Okay, and precision is a collective accurate result. So when we talk about accuracy, it is uh, the uh, the the for example the archery. So archery, the sport archery. So when we talk about accurate, being in the state of accuracy, we're just hitting the target board. Okay, so that we're just hitting the target board anywhere there. When our arrows hit the board, we are being accurate. So, sir, how about precision? When we talk about being precise doesn't just mean hit the target. When you say you're gonna hit the bullseye, then when you let go of your arrow, it will hit the bullseye. When you talk about hitting the nines, the eights, you're basically hitting the target that you really like. So that means being precise. Okay, so when we talk about precision, some of the characters you may know, the ones who are being precise is Merida from Brave, 3D. So it's a fictional character. Also, Hawkeye from the Avengers. It's also a fictional character, but they embody the word precision. So if you don't like the Marvel universe, we have Green Arrow. They are both master in precision, handling arrows. Okay, and if you like a real life person when it comes to precision, we I can give you Stephen Curry from the Golden State Warriors if you're a fan of basketball. Okay, so those people embody the word precision. They embody the word precision, guys. Okay. So next here is what we call the probability limit. So when we talk about probability limit, it is the allowance, or when we talk about probability limit, it is the numerical value allowed in committing error. For example, you're cutting a wood uh, for 100 centimeters or 1 meter. Okay, let's say it's 100 centimeters, but what you just cut is more than 100 centimeters. It's 102. Your papa says it's all right. It's all right. It's within the range. Okay, so it doesn't matter if you cut 102 or you cut 98 centimeters. Both of them are good. Or they belong to the allowed group or they are in the margin of error. So that is what is probability limit. It's a numerical value that is being allowed in committing errors. Okay, so when we commit errors, it is not always perfect, right? There will always be hindrances. Uh, there will always be setbacks. There will always be some kind of a little bit of error, but that's where the probability limit is coming from. You can adjust since you can allow errors to come, and it is only allowed into a minimal. Okay, that is what probability limit is. Next is we have the percent of uncertainty. When we talk about percent of uncertainty, it is also the same as our probability limit but in a percentage form. Okay? So normally they are being used in statistics, in laboratories, and laboratory results. They are being used there. So how much are we going to allow in the excess of fat in your body? Like 10%. So that's how the percent of uncertainties being used. Okay, so probability limit and percent of uncertainty, they are both the same, both same, allowing errors into minimum. Probability limit is it's the numerical amount. Okay, when it comes to percent of uncertainty, it is the allowable amount but in percentage form. Okay, it's in percentage form. Okay, so okay, so let's try to analyze this one. So probability limit is here is an example. Cutting a metal pipe for 100 centimeters with an allowable error of plus negative 5 centimeters. Okay. So that plus negative 5 centimeters from the metal pipe of 100 centimeters is it is allowed to go beyond 100. It can be plus 5 centimeters. Okay, plus 5. It means it's going to uh, uh, 105, and the pipe can be cut measure of 95 to 105 centimeters, since we are given positive negative 5 centimeters. So it can be more than 100 by 5, and it can be less than 100 by 5. So it is in the ratio of 95 to 105 centimeters. And anything more than or less than the probability limit is out of the margin of error. Okay? So did you get it, guys? For the percent of uncertainty, the allowable error will be divided by the actual length and multiply to 100%. So in this case, we have a 5% margin of error, or percent of uncertainty, 5%. So in order for us to fully understand or grasp the idea of having this probability limit and percent of uncertainty, here is an example. We have three pipes, metal pipes. The first one is measured 250 centimeters. The second one is 265 centimeters, and the last one, the third one, is 270 centimeters. So we have three measured metal pipes cut into three different sizes. We have 250, 265, and 270. Again, it's 250, 265, and 270. uh, Okay. So it is uh 250, 265, and 270. Okay. So those are the three measurements of our pipe, of our metal pipe. Okay. And how are we going to get the probability limit in this case, and also the actual length? So what we're going to look for is our probability limit, the actual length, and our percent of uncertainty. Okay, so which of the how are we going to get all those things? Okay, so let's have this one. When we're if we're going to solve for the probability limit, what we're going to do is get the smallest and the highest value that we have and subtract to each other. So we have here 270 minus 250 divided by 2, we will have a plus negative 10. Okay, so probability limit is plus minus 10. If it is the probability limit plus minus 10, then the actual value would be 260. Okay, so 260 centimeters. Okay, so and we're going to get the percent of uncertainty. It is plus minus 10 divided by 260 multiplied to 100%, which is equivalent to 3.85%. So our percent of uncertainty is 3.85%. Okay, so we have here the probability limit of plus minus 10 centimeters, actual length of 260, and the percent of uncertainty, which is equivalent to 3.85. Okay, so that's how you solve or get the value for probability limit, actual length, and our percent of uncertainty. Okay. So next is we have here the vector and scalar. Okay, so among of you guys have idea what is a vector and what is a scalar? What is a scalar? Okay, so sige, I'm giving you guys time to think of what is vector and what is scalar. Okay, so I'll be giving you some time to think, and I'll be back, guys. Okay, so let's go back to business. Here is the vector and scalar. So when we talk about scalar, let's start with scalar. It is the quantity that gives only the magnitude. Okay, so it's just the amount, the reading. It's just the value of our object. That is just the quantity, the value of our object. So when we talk about scalar, some of examples of our scalar is our mass. Okay, so we have our mass. Let's say I'm weighing 90 kilograms. Okay, so that's it. I have the magnitude. I have the scalar value of my mass. Okay, so it is just the magnitude. Another example is the speed. Okay, so the speed just gives you the reading of how fast you're going. For example, my car is running at 100 kilometers per hour in the expressway. Okay. So, when it comes to speed, I just gave you the numerical value of how fast my car is going. Okay. So, it's running at 100 kilometers per hour. Okay. And it's not bad. We have the readings of the speed and the mass. And another thing is we have distance. Okay, so one example is the distance I just traveled 750 kilometers. Okay, so yeah, 750 kilometers. Maybe you're just traveling from norte to south, like that. But from the north of the Philippines to southern Luzon. Okay, so that's why it's 750 kilometers. 7 kilometers. I just traveled 7 kilometers. It's just maybe from Bawan to Batangas. It's just seven, guys. Okay, so that is our scalar quantities. But when it comes to vector, it is not just the magnitude but also the direction. Okay, so for example, let's use also our mass. But in this case, we don't going to use mass, but we're going to use force. Okay, so when it comes to giving the magnitude, we should tend to get or give also the direction. Okay, so for example, the force. Okay, so 90 newtons due east, 90 newtons due south. So we have there a vector quantity in terms of force. Okay, so another example is velocity. So when we talk about velocity, it is giving also the speed. Okay, it's also giving the speed, the numerical value of the speed, but also the direction. Okay, so for example, my car is traveling 100 kilometers per hour due north of the Philippines. So that is a vector quantity. We have the magnitude and also the direction. 100 kilometers per hour due north. So we have the direction, we have the magnitude. It is considered a vector quantity. And lastly, we have the distance also, but it is called displacement if we put direction. Okay, so when it comes to displacement, one example here is I traveled 750 kilometers per hour from north to south. Okay, so that is a legit or a valid example of vector quantity. Okay, so we have the weight or the force, we have the displacement, and we have the velocity. All those three are considered or belong to the group of vector quantities. Okay. So vector representation, it is represented by an arrow. We have here, yes, the traditional arrow. Okay, so lies there is our magnitude. The length of the arrow is what we call the magnitude. It is also called the body of the arrow. Okay. And the next is we have here the tail or the starting point of our vector quantity. And lastly, we have the head, the arrowhead or the direction of our vector is going. Okay, so that's why when it comes to vector quantities, it is necessary that we're going to represent it using an arrow. Okay, so that is our vector representation, an arrow. We have the magnitude, the body, the tail, the star. It is known also as the starting point, and lastly, the arrowhead, the direction of where our uh, magnitude is going. Okay, so we have here the vector addition. So when we talk about vector addition, scalar, you just add values, you just add the numerical value, and you just get the value that you need after you add those scalar quantities. Okay, but when it comes to vector addition, this is addition. It is the method of combining vectors. Combination of vectors. Okay. So let's have here uh, an example or a more distinguished principle when it comes to vector addition. So we have here an example of a arrow pointing to the right, it is also added to an arrow pointing to the right. Okay. So it can be characterized as two arrows to the right. So it don't have any magnitudes. Their red arrows don't have magnitude, but you can add them, and that there will be magnitude of 2. Kasi we combine those two, right? We just add them. Okay, but the thing about it is is when it is in the same direction, you just have to add. Okay, same direction, we have to add. Okay, but sir, the question is, what if we have a problem that there is a different direction of our vector quantity but same value? So when it is in the same value but different in direction, you have to add it. But the question is, add really or subtract? Because we are dealing with different directions. Okay. So when it comes to different direction of a vector quantity, we're going to subtract them. So for example, we have two the arrow the first arrow pointing to the right has a magnitude of 50, and the left arrow pointing to the left has also a magnitude of 50. So since they have both 50 magnitudes, 50 units of magnitudes, then we just cancel them out since they are traveling at an opposite direction. That's why we have here a zero value. So opposite directions meaning subtraction. Okay, so higher values direction prevails. If the right one has the higher value, after you subtract them both, we will use the value of the higher we will use the direction of the higher one. Okay, so if the higher one is from the red going to right, then we're going to use that. Okay, if it is on the left, then we're going to use the left. Okay, so yes, so we have here another lesson, which is the distance and displacement. This is a little early for us, but it's better that we discuss this topic as early as possible. Okay, so we have here the distance and displacement. So displacement is known as total length traveled. Okay, so here is an illustration. If you're a biker or a frequent driver, a frequent traveler from Batangas to Manila, Norte, wala problema. It doesn't matter as long as you know how to read this map. Okay, so as you can see, we have traveled from one point to another in this map. Okay. All the twists and turns, the left and the right, the U-turns, the detour, all of them are considered part of our distance travel. So when we talk about distance, it's the total length traveled. So if you stop and continue, it is also part of the distance covered when we travel. Okay? So as you can see here, from point 1 to point 2, we just traced our directions. Okay? From the starting point up to the final point. Okay? Up to the final point. That is considering all the way that we've been when we travel. Okay, so with that, all the twists and turns left and right is also added, accumulated, and then we have the total distance. Okay, so as you can see here, we have here, yes, we have traveled here a 114-kilometer distance. Okay. So that is what we call uh distance. Total length travel. Okay. That's distance. Next is we have the displacement. So when we talk about displacement, it is the shortest or the minimum length from point A to point B. Okay. From point A to point B. So we have here another map. It's the same map. It's the same map. Okay. We have here point A, and here at is point B. Okay, so guys, do you think of the shortest possible route from point A to point B? Do you have any ideas? which what is the shortest, or how are we going to reach point A to point B in a shortest distance. Okay, so I'll be giving you time, guys, to think. Okay, the shortest possible distance from point A to point B. Okay, okay. Okay, so the shortest possible route for point A to point B is in a straight line. Straight line lang. Straight line. Point A to point B. Okay, so we have to forget all the twists and turns. We're just going to focus on the straight line from point A to point B when if we're going to need to get the displacement. Okay, it's just a straight line, guys. Okay, so here we have let's have an example here. So given a person travels 50 meters to the east, climbs up 25 meters north, turn west for another 50 meters, and another 25 meters south. Solve for the displacement and distance. Okay, so we have here the representation. Yeah, the red dot, as you can see, the red dot is our starting point. So it travels 50 meters east, 25 meters north, 50 meters west, and lastly, we have 25 meters south. That is what we traveled. Okay, so yan yung representation natin. Okay? Okay, so I'll be giving you guys time to answer what is the distance and what is the displacement in this problem. Okay, so you guys, I'll be giving you time to answer and think about it. Okay, so I'll be back. Okay, guys, so let's go back to our lesson. So if you answered for the distance is 150 meters, then you're right. Okay, so if you answered 0 for the displacement, then you're also correct. Okay, so when it comes to distance, we just have to add or accumulate all these distances that we have. So we have here the 50, the plus 25, plus 50, plus 25, which results to 150 meters. Okay, so that is our distance. When it comes to displacement, like I said a while ago, uh, straight line from point A to point B. Okay, but in this case, our point A is also the same as point B, which we have to we have to think about it. How are we going to give a straight line if our starting point and our last point or final point is also the same? Okay, so if you want a little more technical explanation, we have here using the vector addition. Okay, so we have here 50 meters east plus 50 meters west. One is going to the right, one is going to the left, one is going to the east, and one is going to the west. That's why we have to negate those 50-meter value. Okay, and that's why it is being held 0. And the next thing is we have 25 meters north and 25 meters south, which is also 0, which gives us a displacement of 0. Both of them are 0. That's why our displacement is 0. So point A and B are the same point. So that is our starting point and final point. That red dot there is our final and initial point. Okay. So let's have another example here. So okay, so A traveled a distance of 4 kilometers from point O. C traveled 2.5 kilometers due north, then turned to east for another 25 kilometers, starting from point O. And lastly, B traveled a rounded path with a diameter of 5 uh, kilometers, with a diameter of 5 kilometers. Okay, so we're going to find the distance, displacement of A, distance and displacement of B, and distance and displacement of C. So I'll be giving you guys another time for you to answer this. So this is a little quite different from the last time, from the previous example. Okay, so guys, I'll be giving you time. Please try to solve for the distance, displacement of A, B, and C. So here is the drawing, and all of the reference that you need is right here. Okay, so guys, please answer and take time for answering. Okay, so I'll be back. Okay? So, if you let's start with distance for A and displacement A. So if you answer distance 4 kilometers and displacement of 4 kilometers, then you are right. Okay. So if as you see that we have the A traveled only distance of 4 kilometers. So the distance traveled is only 4 kilometers. So that is the distance, the total distance. And for the displacement is it is also the same length as our distance. That's why it is the same 4 kilometers, both of them. Okay. Next thing is we have B, traveled a rounded path with diameter of 5 kilometers. So using we're going to find the circumference of the circle. So using that form, the formula of finding the circumference of the circle, which is pi d, pi d natin, yes, pi and the diameter of 5 kilometers, we will have the answer of 15.71 uh, 15.71 kilometers. Okay? So that is the answer for our distance. And for the displacement, we have 0. For the reason that our starting point and our end point or our last point is the same as our starting point. That's why we just came back from the start, and that's why our displacement would be 0. And lastly, for C, distance C is uh, 5 kilometers. Okay, so why is it 5 kilometers? It is 2.5 plus 2.5. That's why we have the distance of 5 kilometers. Okay, so, and for the displacement of C, it is 3.54. Okay, sir, how did we get that? So as you can see, straight line from starting point to our C, which we can form a right triangle. And if it is a right triangle, then we can use the Pythagorean theorem to get the hypotenuse. It is 2.5 squared plus 2.5 square, which is equivalent to 12.5. But wait, we have to square it again, and we will have the answer of 3.54 kilometers. Okay, so that is how we get or how on how we arrive that is how we arrive at these answers. Okay, so if you didn't get all of this, then then you may practice getting them with these answers. Try and try until you arrive at these answers. Okay, so yeah, let's move on to the next. We have the resultant vector. Okay, so this is the last lesson. Resultant vector. So when we talk about resultant vector, it is a group of vector that can be characterized by a single vector. For example, the C, the component C, from our previous example, it has two vectors, the 2.5 kilometer north and 2.5 kilometer east. So those two are a group of vector. Okay. And it is characterized by our displacement, which is from the point O to point C, which is 3.54 kilometers. Okay. So that is an example of a resultant vector. Okay. So without further ado, let's have an example so we can easily understand this one. Okay, so example 1, vector A from point O has a magnitude of 4 kilometers due east. Then from the end point of vector A, vector B rise to north for 3 kilometers. Solve for the resultant vector. As you can see, we have 4 kilometers due east and 3 kilometers due north. So resultant vector, it is the hypotenuse of the formed right triangle. As you can see, it is just like displacement. So in this case, we just formed a right triangle, and the way we can solve, the only way we can solve for our resultant is to use the Pythagorean theorem. Okay, so we have here r squared plus 8 r squared is equivalent to a squared plus b squared. substituting the value 4 squared plus 3 squared is equivalent to 25. That is r squared. So square both sides. We can get the value of our r, which is to 5, which is 5 kilometers. Okay, so another method here is the Pythagorean the methods in solving for the resultant vector is by the use of Pythagorean theorem, the component method, and graphical method. So graphical method is with the use of graphing paper and measuring all of the possible vectors that will came out. Okay, and the component method is getting the x and the y component, and then get the total um get the total x's and the total y's of our vectors. Okay, so let's move on to the next example, which is this example number 2. So find the resultant vector using component method and Pythagorean theorem. So we have vector A, magnitude of 3 kilometers per hour in the direction of 30 degrees north of east. Then vector B from the tip of A has a magnitude of 2.5 kilometers per hour in the direction of 60 degrees west of north. Okay, so we have that two vectors. So, yan, voila. So we have here the vector A and the vector B. So memorize the drawing, guys, and we will use this one. So first, plot the points in the Cartesian planes, and we just already did. We already plot vector A and vector B. So after plotting the points, get the x and the y components for of points A and B, and that's what we're going to do. Getting the components of A and B. Okay, so let's start off with our first vector, which is the vector A. Starting from point O and ends with point A, this is our vector A. Okay? So since it is an angled vector, it is automatically has x component and y component. So sir, why does it have x and the y component already? It's just an angled vector. Okay, so when it comes to angled vector, it is between the x and the y. It doesn't matter if it is in the first, second, third, or the fourth quadrant. As long as it is an angled vector, automatically there is an x and the y component. Even the horizontal vector, it has an x and the y component. Why, sir? Why does it have a y component? Since it is placed horizontally. Well, it has a y component. The value of the y component is just 0. Okay. Okay. So yeah. So when it comes to angled vector is in between x and y axis. That's why it has an x and y component. Okay, so the angle here is placed 30 degrees north of east. Okay, so north of east, and we have a magnitude of 3 kilometers per hour. So what we're going to do is get the value of x component using the trigonometric function. Here, xa is equivalent to 3 cosine 30. So why is it cosine? So why did we use cosine? So as you can see, we have here the vector which has having 3 kilometers per hour as our hypotenuse. And our x component is the adjacent of our angle, which is 30 degrees angle. 30 degree angle. Okay. Cosine has a principle of having the adjacent side over the hypotenuse of the triangle. So as you can see here, we have the adjacent side of our 30 degrees is our x component. That's why x component divided by the hypotenuse, which is 3, is equivalent to cosine theta or cosine 30, which is our degrees. Cross multiplying, this is the shortcut now. XA is equivalent to 3 cosine 30. And the result will be XA or our x component at vector A is 2.6 kilometers per hour. Okay? Next, So this is the complete representation of our vector A. We have the x component, the y, the angle, the point O, the point in, the 3 kilometers per hour magnitude of our vector A. So let's get the component, y component. So using also the same trigonometric function, we have here ya, the y component for vector A, which is 3 sine 30. So sine theta here is has a principle of uh, opposite all over the hypotenuse. So if our 30 degrees is the adjacent of our x, now the opposite side of our 30 degrees is our y component. Okay. So our 30 degrees opposite side is our y component. Okay, so ya all over hypotenuse, which is 3, is equivalent to sine 30. Cross multiply again. After cross multiplying, we will arrive at the answer of 1.5 kilometers per hour. So recap, we have 2.6 kilometers per hour for XA and 1.5 kilometers per hour for YA. Okay, so that is for our vector A. So let's proceed in getting the x and the y component of vector B. So for vector B, we have point A, as the problem says that the vector B starts at the tip of point A. Okay, at the tip of point A. So at the end of point A, there is point B. So since it's also an angled vector, it is automatically that we have x component and we have y component. So basically it is the same, and we have an angle of 60 degrees west of north. Okay, so west of north. So we have there 60 degrees and a magnitude of 2.5 kilometers per hour. Okay, so let's get the x component. X component is xb, x component of vector b. We have 2.5 sine 60. So, sir, why did we use sine? A while ago, we just use cosine for x. As you can see, the orientation of our angle is different from the orientation a while ago. Why? Because the adjacent side of our angle here is y component. So the opposite of our angle is our x component. That's why we use sine. Opposite over hypotenuse. Xb all over 2.5. Cross multiply 2.5 sine 60 is equivalent to our x component. The result will be 2.17 kilometers per hour. Okay? So next is we have the y component. The y component has consist of 2.5 cosine 60. So here it is. The orientation of our angle is beside or is at the adjacent of our y component. So it is just rightful that we use cosine, since the principle of cosine is adjacent all over the hypotenuse. Our adjacent is our y component b, and all over 2.5 cross multiply to cosine 60, we will have 2.5 cosine 60, which is equivalent to our y component at vector b, which will then result to 1.25 kilometers per hour. And last, we have the recap of xb and yb, which is we have 2.17 kilometers per hour and 1.25 kilometers per hour respectively for x and b, for x and y. Okay, so combining the x and the y component. So let's start with x component. Combining or adding the x component, we have here the xa, which is 2.6 kilometers per hour going to the right. And going to the left is our xb, x component of b, vector b, which is 2.17 kilometers per hour. Okay. Different directions and different value of our magnitude. So since they have different directions, we just going to subtract, right? 2.6 kilometers per hour minus 2.17, we have 0.43 kilometers per hour. A while ago, I said higher values direction will prevail. Okay, so the higher value here is 2.6, which is going to the right. then our 0.43 kilometers per hour is also going to the right. Okay? And next, we have the addition of y component. So, YA is equal to 1.5 kilometers per hour and YB is equals to 1.25 kilometers per hour. Both of them are going up, going upward. If they are both going upward, we're just going to add both of them 1.5 kilometers per hour plus 1.25 kilometers per hour, which will then result to 2.75 kilometers per hour. The direction, both of them are going up, so as our final answer of 2.75 kilometers per hour. Okay. So yes, we have the x value of 0.43 kilometers per hour. We're just going to plot again this 0.43 and 2.75 kilometers per hour. So here is the final drawing of our component, and we're going to represent this x and y component, total x and y component, into a one single vector, which is our resultant vector, from the starting point up to the end point of our two vectors, vector A and vector B. Okay? So, here's our resultant. And using Pythagorean theorem, basically, this is it. We can literally get the final answer in this problem using the Pythagorean theorem. So it is a squared plus b squared is equivalent to c squared. Substituting the values that we have, 0.43 square plus 2.75 square is equivalent to c squared. And we have here the value of our c, which is 2.78. So we have here 0.43 square plus 2.75 square. The answer is 7.7474. Square root of our answer will give us 2.78 kilometers per hour. Okay? So we have our resultant of 2.78 kilometers per hour. But wait, this is a resultant vector. If it is a resultant vector, it is not just the magnitude. We need to have our direction also. So for us to have the direction, we're going to use tangent theta, opposite all over adjacent. Our opposite here is 2.75 and our adjacent is 0.43. Using the tangent principle, opposite over adjacent, we can get the value of our uh, angle, which is tangent 2.75 divided by 0.43, which will result to 81.11 degrees north of west. Okay. So we have here the value of our resultant, which is 2.78 kilometers per hour, and the value of our direction, which is 81.11 degrees north of west. Okay. So I'll be posting this, guys, in our LMS. I will be uh, I will be posting this so you can watch this over and over again, and at the same time uh, you can uh, rely on this as our what to call this, our lesson. Okay, I hope you guys understand, and if you have questions, just ask. Okay, so question starts right now, and I'm gonna end this video right now. So bye, guys, thank you for attending the class, and see ya.